Okay, so this video is about the mean value theorem. And before I explain the mean value theorem, I want to explain first Rolle's theorem. So Rolle's theorem says this. It says let f be a function that satisfies the following three hypotheses. For example, well, for one, f is continuous on the closed interval. So you got some function at a and at b. The function is continuous, meaning that it has, you don't have to lift your pen or pencil off the page to get to from one point to the next. So it's continuous from A to B. Then it says on a closed interval, so it means that at A it exists and at B it exists. So that's closed dots, not asymptotes or anything like that, or holes there. Part 2 says f is differentiable on the open interval from A to B. So basically it says here is closed, so A and B are existing, but and it is equal to A or B. However, on the open interval means that it doesn't have to be differential at A or B. So it doesn't have to be differential at the endpoints. This is all the points in between there. And then the final thing is f of A equals f of B, meaning that the output at A should be the same output at B, as in they have the same y values on both ends. And if all three of those is true, then there's a number C in A and B on the interval from A to B such that f prime of C is 0. As in, there's a horizontal tangent at some place that's 0. So the slope at some place in that graph is 0. So in the graph I just drew, clearly I can see there's a horizontal tangent there that's 0. And I got a second horizontal tangent here. It's also 0. So clearly that does exist in the graph I just drew. So let's talk about that again with some numbers. For example, all right, let's start with this problem. All right, this problem says verify that the function f of x equals x cubed, subtract x squared, subtract 6x plus 2, satisfies the hypothesis of Rolle's theorem for the interval from 0 to 3. Then find all c values that satisfy the conclusion. All right, so first of all, this is a polynomial. So I know this polynomial is continuous. So all polynomials are just continuous functions. So I know it satisfies part f. It's continuous on that interval from 0 to 3. The other part says, is it differentiable on the interval? All right, so being a polynomial, all the points should not be corners. It should be smooth. Like it should be a smooth curve from one point to the next in a polynomial. Polynomials don't have any corners in them. They won't have any vertical asymptotes in them. They won't have any oscillations in them. All those places that you have places of discontinuity. And the last step is, so this is satisfied. The last step is prove that f of A equals f of B. So A and B are the endpoints. So what I want to now know is f of A equal to f of B? So let's find f of A. A will be 0. So f of 0. F of 0 should be, that becomes 0, this becomes 0, this becomes 0. F of 0 is 2. So that was pretty easy. The other thing I want to find out is f of 3. So considering f of 3 requires a little bit more work. So it's going to be 3 to the third, subtract 3 squared, subtract 6 times 3, plus 2. So 3 to the third is 27. Subtract 9, subtract 18, plus 2. All right, so 27, subtract 9, but subtract 9, subtract 18 is 27. These two have some negative 27. So negative 27, positive 27, this goes to 0. So the output is just 2. So f of 0 and f of 3 both equal 2. So it satisfies all the statements, all the given statements, hypothesis for the mean value theorem. So it's true. It does satisfy, meaning that at some point on this interval, they should have a c value that has a horizontal tangent, the derivative at c should be 0. All right, so let's find it. So the second part of the question says, then find all c values that's satisfied for. So let's find them. So the function is f of x equals x to the third, subtract x squared, subtract 6x plus 2. And the derivative should be 3x to the second, subtract 2x, subtract 6. And we want to know when that's equal to 0. So we want to know when is 0 equal to 3x to the second, subtract 2x, subtract 6. All that's divisible by 3. Well, actually, it's not all divisible by 3, because the 2 isn't divisible by 3. Also, it may be factorable. I could take the 3 and multiply it to the 6 and see if it's factorable. That's going to give you 18. And I don't think there's any numbers that multiply by 18, but also add to be 2. So because of that, our best way of answering this is going to be quadratic formula. So you should wind up having 2 plus or minus the square root of 4 subtract 4 times 3 times negative 6 all over 6. So essentially this is going to be 2 plus or minus square root of 76 over 6. And square root of 76 is roughly 8 point something. It's roughly 8.7 all over 6. And I'm out of space, so I got to erase some of this. So this is what we know. All right, so this is going to wind up giving you 10.7 over 6 and negative 6.7 over 6. So 10.7 over 6 is about 1.8. And this is negative. It's about negative 6.7 divided by 6. It's about negative 1.1. Because that's not on the interval 0 to 3, we don't need that one. It doesn't fit in between 0 and 3. So what we know for certain is there is a c value that makes that is going to have a horizontal tangent, and that's going to be at around 1.8. That's a rough estimate because I square rooted that and estimated the decimal. All right, anyway, so that is an illustration of the mean value theorem, of Rolle's theorem. I can give you an example of one that doesn't fit Rolle's theorem. One that doesn't fit Rolle's theorem, would be disproved by Rolle's theorem, would be this. All right, given this question, it will say verify that this function does or does not satisfy Rolle's theorem. I know it doesn't satisfy Rolle's theorem because the interval is from negative 1 to 4. So negative 1 to positive 4 is the interval we're looking at. And on that interval, x equals 0 is included, right? And x can never be 0 in this function because it makes a 0 come in the denominator is undefined. So this function is some kind of graph that probably does something like this. And it's not continuous. So it doesn't fit Rolle's theorem because it's not differentiable on the interval because it's not continuous there. You can't get a derivative there at that asymptote. So that would be example one that does not fit Rolle's theorem. Does not satisfy Rolle's theorem. All right, let's go. Last thing is the mean value theorem. So let's do that now. So our main use of Rolle's theorem is to prove, in the event we need to prove something, is to prove the mean value theorem. All right, and the mean value theorem says this: let f be a function that satisfies the following hypothesis. 1, f is continuous on the closed interval from a to b, and 2, f is differentiable on the open interval from a to b. So basically the first two parts of Rolle's theorem. The third part we don't need for mean value theorem. And it says if all that's true, then there is a number c in the interval from a to b such that the derivative at c is equal to the slope from a to b. Essentially what that says. Or equivalently, if I multiplied this both sides by b subtract a, you'll wind up with this formula. So I don't really use that very much, but that's true. So basically this is what the mean value theorem says. So let's actually use it. Let's actually go to the example where we involve the mean value theorem. All right, before I actually use the mean value theorem, let's look at an illustration of the mean value theorem. Basically what it says is, at some number c, you have a slope there at that place that's equal to the slope from a to b. Notice how these two lines are parallel to each other? So they're parallel to each other, that means the slopes are the same. So mean value theorem that says that if 1 and 2 are satisfied, then the slope from a to b at some point on the interval from a to b is going to equal to the slope of f at c. So that's going to be true there. Here's another example. There's two places where those slopes are the same. So here, this slope and this slope are all equal to the slope from A to B, which is the blue line, if you can see that. But yeah, that's the illustration of mean value theorem. And a lot of times with these definitions, it's good to see an illustration of it to make better sense. All right, now let's actually do it with the problem. All right, so this is the question. Verify that the hypothesis of the mean value theorem is satisfied on a given interval and find all the values of C that satisfy the conclusion of the theorem. All right, so let's verify the hypothesis. First of all, this is a square root function. If you graph any square root function, it's generally look like this. So it's going to be continuous. If you try that square root function at 0, that square root function is going to be, actually that one shifted up a bit. If you graphed it on a calculator, you'd see that it looks more like this. It shifted up 1. So it would be this function. It starts at -1, and then it goes over. And that would be the function. So from 0 to 3, it's going to be continuous there. So that's true. If I started at 0 and I went to 3, it's continuous and exists at all those places. Also, it's differentiable every place on that interval from 0 to 3. So the two hypotheses are true. What we want to verify is the conclusion. And our conclusion says this. I'll write it. So the conclusion was then f prime of c equals to the slope from b to a. So this is what we want to verify, because we already verified that the hypotheses are true. Now we want to find the c values that make those two slopes the same. So basically, the original equation is this: alpha of x equals to the square root of x plus 1. So the derivative there should be 1 over 2 square root of x plus 1. You can look up why, but that's what the derivative of that function is. That's important to know. And what we want to find out is the value of f of b, right? So f of b. In this case, b is 0. Actually, b is 3. This is a, and this is b. Let's make that look better. So again, this is a, and this is b. So b is 3. So I want to find f of 3, and I want to find f of 0. So f of 3, and I want to find f of 0. F of 3 would be the square root of 3 plus 1, which is square root of 4, which is 2. F of 0, square root of 0 plus 1, which equals to square root of 1, which is 1. So I know f of b, and I know f of a, that's 2 and 1. So I know that this derivative should equal to 1, let's change the color. Well, I'm going to have a hard time trying to squeeze it in this little space here. So if you would, write down everything you see on written, and I'm going to remember what they are too, and I'm going to use this. I'm going to erase all of this so I can actually finish the problem. So go write it down. I'm going to erase the screen right now. So the derivative was 1 over 2 square root of x plus 1, and that should be equal to f of b subtract f of a over b subtract a. So b was 3, so it's 2 subtract 1 all over 3 subtract 0. So that's 1 over 3. So that means that 1 over 2 square root of x plus 1 has equal to 1 over 3. Since both of those are underneath 1, I could simply say that 2 square root x plus 1 has equal to the denominator, 3. So those two denominators have equal to each other because they're true fractions. So that means that the square root of x plus 1 equals to 3 over 2. And if you square both sides, you should wind up having 3 over 2 squared, which is x plus 1 equals to 9 over 4. So if that's true, x is 9 over 4, subtract 1, which is about 1.25. X is what we call in C. So C is 1.25. This is the place where the slope between A and B is equal to the slope at the derivative of f of 1.25. Anyway, that's all I have. Good luck.